title is Abstract Structure of Unitary Oracles for Quantum Algorithms. Please,
Good morning, everyone. Thank the organizers for having a really great time. Sad it's the last day. But today I'm going to talk a little bit about some approaches using this strict symmetric nodal category framework to address quantum algorithms. So yesterday in Jason's talk, he said, oh, wouldn't it be really nice if we could use these categorical structures to say, well, we've got some particular structure in our category. What does that tell us about the algorithms that we can build using process theories that exist in that category? And so what this work tries to do is make some first steps in that direction. And so we'd like to prove that this abstract structure is useful by finding some new quantum algorithms using it. And so we've got kind of a moderate first result on this. And this is work that I've been doing with James Baker over here, looking certainly into that. So the first structure that we want to look at in the abstract setting to try and say something useful about algorithms are black box oracles. So black boxes occur in quantum algorithms and also in classical algorithms, very common structures. But they're just something that has a series of inputs and outputs where you don't know what's happening in between. It's just some kind of black box. So most known quantum algorithms that are useful and provide a big speedup actually have this same structure. They're oracle algorithms, such as Schrodinger's algorithm, Thor's algorithm, Grover's algorithm, is really well known ones. So I said that black boxes have no structure, that we don't know what's happening inside. But when we try and realize them in some kind of actual process theory, such as quantum mechanics, then they provide some structure on top of this kind of unknown black box. And in the case of quantum theory, then these black boxes need to become unitary. So this is the abstract structure that I'm going to analyze first. So the main questions of the talk are, what should the abstract structure of these oracles be? And secondly, can we take advantage of the abstract setting to try and gain some new insights? And the first new insight will be kind of this new quantum algorithm. The second will be applying this unitary structure in a new process theoretic setting. So we'll start with something everyone probably knows decently well. So this is the traditional circuit diagram for the Schrodinger's algorithm. We've got our input initial states. There are two systems, one on the left, one on the right. And in all my diagrams, I'm going to be reading from the bottom to the top. So that's why the circuit side. Then we've got some kind of black box oracle, which in this setting really is a black box. It doesn't have any specific structure. Then we perform another Fourier transform as a measurement on the left system, and we don't do anything with the one on the right. So the first thing we'd like to do is look at what this, so this is an algorithm, it's a process, which means it's a morphism in Eto. So we want to look at what that process actually is using our diagrammatic framework. And actually, Jamie looks at this algorithm, Grover's algorithm, his algorithm, in another paper called Topology of Quantum Algorithms, so you can look that one up. I'm not going to spend a lot of time on this in particular, because I just want to focus on the oracle itself. So we see that the oracle itself needs to have some kind of mathematical structure, and that's because this structure is going to ensure that it's unitary. So we'll just focus on the oracle. So our theorem is that oracles with this abstract structure, and I'll detail what parts of this are in the coming slides, are going to be unitary in general, not just in the setting of quantum information or Eto. So the first little piece we'll need is we'll need to define special dagger convenience algorithms. So these are, they obey all of these diagrammatic rules, either associative, unital, commutative, special, convenience law, and these correspond to an observable, or basis Eto. And as a result, by Bob and Duncan, we define that two observables, we'll color them differently, when we have different ones. So there's two dagger convenience algorithms here. One is white, and one is gray. And when we compose these morphisms, we know that they're equal to this kind of disconnected diagram here. And this is what this kind of is the general abstract structure for when two observables are complementary. So just to give a quick example. So in Eto, category of open spaces, fine-dimensional open spaces in linear math, comes every pair of complementary observables. You can get a pair of complementary observables that come from finite abelian groups. So what we do is we take the group elements and say that each of them is one of the basis elements. the Frobenius algebra using the copying. That's copying, that's upside down. Yeah, I apologize. The picture's here upside down. So this one should be 1 and then go to the top. So you take one basis vector and you just copy it, or you delete it. And then another Frobenius algebra that's complementary to that, so it obeys this, is given by the group multiplication, the multiplication of the group that you use to define the basis elements. And again, these pictures are upside down. I apologize. By the way, ask questions. Sure. Yeah, so this is the one here is the identity, the monoidal unit. And here, this should be the identity element for, oh shoot, wait a minute, yeah, it's a bit funky. So this should be from the identity, yeah, this is incorrect. This should be from the monoidal unit to the identity element group. Yeah, maybe I'll write it quickly. So from the monoidal unit to the identity element group with some scale. Yeah, good catch. Cool. So the next thing I need to define are these classical maps. So when we have these black boxes, we've got this just generic structure, which in the Deutsch-Torsi case, for example, is it's some map that's either constant or balanced. And we want to capture that structure. So what these things should be is they should be maps between bases. So that means they're maps between observables. So in this case, maps between vector Frobenius algebras, the black one here and the white one, which should obey two rules. So this is the rule that's comonomic homomorphism, and the second is that it should be self-conjugate. And this is what we call classical maps. So what I want to now show is that with this kind of setup, we can always define unitary oracles that have the structure that showed up in that Deutsch-Torsi algorithm I showed previously. So what we need are 3 vector Frobenius algebras, a gray one, a white one, and a black one. A pair of these are complementary, so in this case, let's say the gray and the white. And we need a classical map that goes from the black one to the gray one. So in this, if we have all of these objects, then we can always produce a unitary morphism that looks like this. In any category. So the proof goes like this, and I'll show it because it's kind of a fun diagrammatic proof. So unitary means that we compose it with its dagger, then we're going to get the identity. So we take this and we flip it upside down, the whole thing, and put it on top of it. So this looks like this, and what we want to show is that this is equal to just 2 wires. So the first thing we can do is we can expand out here, just using the spider rules. So we do the same on the left-hand side. So now we, remember this is self-conjugate. The Frobenius homomorphism rules. So I can pull this around the top and turn black into gray. That shows as gray. It's a little bit hard to see, so that should be gray now. And we also know that it's self-conjugate. It's self-conjugate homomorphism. And then here I'm going to use associativity between this and here. So I'm going to move this one to the left, and this one to the right, this back. So, and now I can pull down, and I see again that I can use my comonomic homomorphism rule to pull these 2 morphisms through this black dot to get one gray one again. And what we have here is exactly the complementary condition. So I said that white and gray were complementary. That means that I can disconnect them. Homomorphism again. And now these are just 2 uniform rules on the 2 Frobenius algebras to get the identity. So what we've shown is we've defined, you happen to be using diagrams, it's actually in the categorical framework in general, some abstract structure which is required to make oracles physical, which in this case means unitary. But you can define unitary not in F-code. This isn't specific to quantum mechanics. It's true for any process theory that obeys this general structure. Yeah. The next question you'd want to say is, well, can we take, that's wonderful and everything, perhaps I can argue that it's elegant and it looks nice, but can we take advantage of this abstract setting to gain some new insights? And what I want to argue is is yes, and it's kind of a larger program. I want to keep working on this. So the two results I'm going to talk about here are that we can develop a new group theoretic algorithm for solving a problem classically. And second, we can take advantage of this general setting to see unitary oracles go through in a setting that isn't quantum information, which is what was originally inspired by. So the first one. This is the problem we're going to look at. It's the group homomorphism identification problem. So you're given two finite groups, one of which is abelian, and a black box function which is a homomorphism into the abelian group. But I haven't told you which homomorphism it is. And I ask you to find out which homomorphism it is. And I ask you to do that by making the least number of queries of that homomorphism that you can. So identify what f is by calling it as few times as possible. So we're going to need a little bit more structure in order to analyze this problem. So the first thing I want to mention is, well, what do group homomorphisms, group representations look like? So in the case of an abelian group, these representations are one-dimensional, so they're just mapped to C, which is the Monod unit in FO. So it just looks like a morphism from one system to blank, labeled C suggestively. And in the case of non-abelian groups, then this is a map from homomorphism from the group into matrices, n by n matrices, depending on what the dimension of the representation is. So this is an n-dimensional representation. And we can see these group representations as measurements. And this is because what they are projections from the Hilbert space onto some smaller space. So in the case of abelian ones, representations give, just to give you a number that you can then take a complex conjugate of to get the probability. And in this case, they'll give you a subspace equal to the same thing. So they're based on rules. These are just the normal kind of rules for group representations, which is that they act like homomorphisms. And this is what we'll draw for matrix multiplication. I won't go into too specifics about this, but and also what they do with the unit of the group. And this is just that it sends the unit of the group the identity. So this is another morphism, and this is the algorithm. So again, we can represent algorithms as morphisms in the category, which means that they have some specific picture. And I'll talk a little bit more about why I like this in a bit. But I'm also going to specify that the general algorithm that I defined is a map into any abelian group. But now let's consider A to be a cyclic group of order n. So that in particular means that the cyclic, well, the piece here. So this is our homomorphism from some, so there's a group G, which is the basis of the wire on the left here. And there's another group A, which is a cyclic group, which is forms the basis on the wire on the right. And so since this is a cyclic group, that means that the representation here is going to be one-dimensional. But G is not necessarily abelian, so we have some kind of n-dimensional representation there in general. And the Frobenius algebra structures here are the examples that I gave earlier. So this black one is the copying map for G, and this one here is the group multiplication for A. And we know that this whole thing is going to be a unitary operation because of the proof in the original part. So we've written down some morphisms, and we can say, well, in a lab, what we do is we have this system on the left, we have two systems, we prepare some states, we send them through some unitary, and we measure in the representation basis. So what are we actually mathematically computing? Why? And that's sort of the question, right? So what is the algorithm we're actually doing? So we can do, again, some diagrammatic simplification. The first thing we want to do is use the fact that we can pull homomorphisms through the group multiplication, but also representations through group multiplication. And that's also going to flip this guy upside down when we pull it through. And what we see is that the system on the right, which we're going to basically ignore, is just totally disconnected from everything that happens on the left. Thanks to just normal spider rules, and just combine these scalars, one, and then we can pull around again. So here now, here I'm just pulling these two around here. can see that this setup that I did in the lab, which I had to draw as if it was unitary operations, actually is mathematically computing whatever this is. So take a look at what this actually is. So this is just the flip and conjugate, the transpose of rho after f. And this is also going to be an irreducible representation of A. And this is a representation, and this is a homomorphism, so you compose them and you still have another representation. Oh, geez. Yeah. Is that right? Yeah, that's right. We flipped that twice. I apologize. So this is an irreducible representation of G. And so what we can do is choose rho to be a faithful representation of A. So what F does is it turns representations of A into representations of G. This should be a G here. So this means that so what we're doing here is we're measuring this composite in the representation basis. So if we measure this, then we identify exactly what this, so since rho is faithful, this means that rho after F is equal to rho after F prime only if F and F prime are equal. So this means that measuring rho after F will identify F up to isomorphism. However, it's the case that for one-dimensional representations, they're isomorphic if and only if they're equal. So that means that if we measure this in the representation basis, we exactly know what F is going to be with a single query. So we can now move beyond the case where A is equal to a cyclic group. And we can generalize this using proof by induction via the normal structure theorem on abelian groups. So every abelian group is a product of cyclic groups. And for each one of these cyclic groups, it only takes one query to identify the group homomorphism. And so we simply run the algorithm one time for every factor in the structure theorem decomposition of A. So if there are k factors for A, then in k oracle queries, we're going to be able to identify F. So one thing to note is that the naive classical solution, so the way you identify F, you just have some kind of classical computer, is to look at G and to, on every single generator of G, take a look at what happens to F. So this is going to depend on the number of factors of G. So the classical algorithm depends on the factors of G, and the quantum algorithm depends on the factors of A. So if we have a very large number of factors in G, then we're going to get a big speed up in the quantum mechanical phase. So another point I'd like to, this is nice, we found some new algorithm. But another thing that's nice to notice about the fact that we found a new algorithm is also what it does in terms of relating our structure to other algorithmic structures. So in this paper that I mentioned, James' paper that I mentioned earlier, I won't go through the details, but this is the picture for the hidden subgroup algorithm. And we can actually see our algorithm in relation to it. And so what we do is we actually say, well, this input, which is just the identity for the group, is actually equal to a superposition over all of the representations. So in the hidden subgroup case, we're just putting in some kind of distribution over all possible representations. And in our algorithm, we say, well, can't we take advantage of the information we get by choosing some particular input representation? And then we ask, well, what's the advantage we can gain? And we do some diagrammatic simplifications, and we get the algorithm I just showed you. So we kind of get two things out of the framework. One is we can find some kind of new quantum algorithm, and secondly, we can understand the relationship between existing algorithms. And it's actually kind of understanding the relationship between existing algorithms and taking advantage of, sort of free information that we can find new ones. So the second thing I'd like to talk about is an application of the original unitary theory to a category that's not quantum information. So Baez, Erleve, and Fong have been working on signal flow theory, which is sort of a general theory of electrical circuits, categorical framework of electrical circuits. And this information flow in electrical circuits. And this happens in the category of linear relations. And find the following way. So we've got the objects are high-dimensional K-vector spaces. Morphisms are linear relations. signal flow calculus, there are some structures that that come into play. So they've got an addition monoid and a copying comonoid and a multiplier here. So it turns out that both of these, I'm not going to go through it, but this is in the paper. Both of these can be turned into Frobenius algebras, and in particular, they can be turned into dagger Frobenius algebras. And also, they turn into complementary dagger Frobenius algebras. So there's a structure that appears in their work, and that's a structure for a resistor. So what we have is sort of the left system here is the current variable in the electrical circuit, and the right wire is the voltage variable in the electrical circuit. So this is just an Ohm's law resistor in their framework. But we can see that it has the exact same abstract structure as the unitary that I spoke about in quantum information, the unitary oracle is. We need this multiplier to DSL conjugate homomorphism, which it in fact is. So that means that if I were to take a dagger of this and stick it on top, it would turn out to be the identity. Now, what exactly does this mean in terms of electrical circuits and signal flow? Well, it means that I suppose at some level, the information in Ohm's law is versatile. So that's nice. But the main point is just that there is some use in taking structures in quantum information, putting them in this framework, and then looking in other process theories. And it turns out you see the same structures, and you might get more useful results than this, but it's good to find first examples. So the first thing we did is we proved this theorem about a pair of complementary dagger Frobenius algebras, which are equipped with a classical map from the third. We proved that this is unitary. This gives us an abstract understanding of an oracle in quantum computation and in other process theories. We apply this to develop a new algorithm for the deterministic identification of group homomorphisms into abelian groups. And we find the same structure that happens here in the theory of signal flow. So the real big idea of the talk is that this symmetric mineral categorical setting, with or without diagrams, I like the diagrams, not strictly necessary, productively unify process theory at an abstract level. So that means we can talk about multiple process theories using the same language, and we can do so productively, which means we can then go back and contribute and find new algorithms in whichever setting we have an interest in. And also, like an hour ago, we're on the archive. Thanks very much for your time.
So, questions? Yeah.
So, well, you showed that if F is a classical map, then that suffices to make the oracle unitary.
Yeah.
You didn't show the converse. Is it an infinite way?
If F is a classical map? Yeah, so
if that unitary is unitary, can you derive that F is a classical map?
So if it's unitary and you've got complementary, like you've got the same complementary structures, then yeah, it should be. And it's also the case that if you don't, like if you replace, this is kind of a result. We drop the F here and make this the identity. So this is just a wire. Then it's an if and only if statement is that this morphism dagger is unitary if and only if white and black are complementary. The type relationship between these kind of pictures and complementarity and stuff.
Is there any other question? Yes.
I'm just kind of curious about the resistor thing. I mean,
Yeah, me too.
so does this mean there's some kind of electrical component that reverses the action of the resistor? Or is this to be taken in a more abstract setting?
Yeah, so I think it's a more abstract, I would take it in a more abstract setting than that. So this actually doesn't say something about there being a real physical component. It says something about the laws, it says something about Ohm's law, actually, more than it says something about a physical resistor, is the way I would take it.
Can they do translate those two?
They're working on it. So I think so, right, in terms of sense, the next thing they want to do is take a look at, they're working on capacitors right now, and then inductors. And I want them to, so So people have these funny, experimentalists use these quantum circuit frameworks, which are kind of like hybrids in between normal electrical circuits with nonlinear elements. And I think it would be really neat to try and find some kind of in-between, because I've already got these pictures with quantum algorithmic flow, and then if we take these sort of pseudo circuits and merge them, it would be quite cool.
So this is one way that you might look inside a black box oracle, and one way of thinking unitary and so on. Is there any reason to think that this is the only way to do it, or is it just the simplest way?
Yeah, I think there should be other ways of doing it. This is the way you always. I guess the reason for the original interest in this particular, and it's way back here, in this particular structure, is that this is the way it's done in the lab and in every traditional, but this is the exact structure that's used. But I think that there could be other ways of creating unitaries out of classical maps. And I would argue that actually this would be probably a good setting for exploring what those would be.
Yes, Bob?
So, do you know anything from the structure about genuine speed up of quantum as compared to...
Just in general?
I mean, do you learn something about when do you have speed up?
Yeah, so I mean, an interesting point is that so when you look at all the algorithms that I've mentioned basically in this talk, the one that we do, Grover's algorithm, the hidden subgroup algorithm, George Stroh's algorithm, they all look like this. The pictures are almost all exactly the same. I mean, you kind of twiddle a little bit what happens here and here. And I would say the very simple thing this says is not a surprise, but it's that all the kind of quantum algorithms that we find useful seem to use the same trick. And what this does is, by putting them in kind of this nice, like drawing the morphism out and seeing that it's the same picture, I can get a picture for what that trick is. So if we want to have hidden subgroup speed ups, if we want to have this group ID speed up, then what I need is any process theory that has complementary observables in classical maps. Any dagger. So as long as I have, so it's nice, I can point to these structures in the process theory and say that it gives me automatically, these are the algorithms that are going to work and give me a speed up.
Okay, I think we should now move to the next talk, so let's thank Will again.